In this section, we're going to look at absolute value functions. First, we'll graph absolute value functions, then we'll solve absolute value equations, and finally, we'll solve absolute value inequalities. An absolute value function is a piecewise function. And when you look at the graph of any absolute value function, it always has this shape. It's V-shaped. And so there's two pieces to the graph, one side of the V, which has a positive slope, and the other side of the V, which has a negative slope. So the classic absolute value function, absolute value of x, can be defined like this. F of x is equal to, well, if we think about this piece on the right, what is it? It's a line that has a slope of 1. So if you think of y is equal to mx plus b, the slope of the line is 1, and b, the y-intercept, well, it intersects the y-axis at 0. In other words, the right side of the v has the equation f of x, or y, is equal to x, if x is greater than or equal to 0. On the other side of the v, on the left side of the v, we can see we also have a line, y equals mx plus b, but the slope of this line is negative 1. And so for that piece of the graph, y is equal to negative 1x plus 0, the y-intercept is 0, if x is less than 0. And so that's the classic definition of the absolute value function. It's two lines, one with a positive slope and one with a negative slope. Let's take a look at some variations on this graph. Let's find the equation of this function. Well, if we look at this function's graph, we notice that it's the same as the absolute value function, but what has happened to it? The vertex usually is here at 0, 0. But instead, it's been shifted to the right 1 unit, and it's been shifted up 2 units. And again, the way we know that is because the vertex is usually here at 0, 0, and if we look at where the vertex of this graph is, it's at 1, 2. So shifted to the right 1 unit and up 2 units. Now remember, we looked at transformations of functions in section 1.5. So for this function, in order to shift it right 1 unit, we would take away 1 inside from our input, and then to shift it up 2 units, we would add 2. So just as a reminder from what we learned from the last section, subtracting 1 is what we would need to do to shift it right 1 unit, and adding 2 is what we would need to do to shift it up 2 units. And so this would be the equation of this graph. And if you wanted to confirm that, you could just take some technology, a computer using Desmos, your graphing calculator, and graph it, and you would see this is the graph that you would get. Do they get any harder? Well, let's compare our next graph. Now this is also an absolute value function. It has the classic V shape. If we look at the vertex here and compare where this vertex is from where we would normally expect it, we know that this vertex has been shifted right 3, and it's been shifted down 2 units. So it's been shifted to the right 3 units, it's been shifted down 2 units. And so we could start writing this function. F of x is equal to, all right, so just like before, if we want to shift it to the right 3 units, we would subtract 3 from the input. And if we want to shift it down 2 units, we would subtract 2. But we're not done. Why? If you notice, this graph the slope of this graph is not our traditional absolute value slope. If we go back and we look at the traditional absolute value graph, the slope of this graph is 1. And if you look at this graph, the slope of this graph is not 1. What that means is, and if you think back to our transformation section in our last section, in section 1.5, that there's been something that the function has been multiplied by in order to stretch the function vertically. The easiest way to do this is just to look at the slope of this graph. If you look at the slope of this line right here, this line has a slope of 2. And so the multiplier here is 2. And so this equation of this function is f of x is equal to 2 times the absolute value of x minus 3 minus 2. So to summarize, absolute value functions are piecewise functions, always shaped like a v. The classic absolute value function looks like this, a v where the vertex of the function is at 0, 0. We can shift that function, and we can find the equation of this function simply by thinking about how the shift was done and then adjusting the equation accordingly. And finally, in the last example, not only was the vertex shifted, the slope was also shifted, and we can adjust that by simply putting the new slope in as the multiplier. And that's all there is to the graphs of absolute value functions.